My name is Linda Young, and this is my presentation for Lab 2. The purpose of this lab was to analyze the effects of gravity and drag forces on a falling object, utilizing and comparing an observed model and a computational model via Tracker and GlowScript. I had to create two models, one of them showing the effects of only gravity, and the other showing the effects of both gravity and drag force. The main principle studied in this lab was Newton's second law, which states that the acceleration of an object is directly proportional to the net force and inversely proportional to the mass. I used Newton's second law in the lab by using the momentum principle, which I derived by dividing by mass to get the velocity update formula. I then was able to rearrange the position update formula as well, which I will show later in my code. I had to calculate the net force, and to find the net force in the system or any system, you have to add up all the forces acting on that system. For this particular lab, I had to calculate both gravity and drag force. Gravity, also known as weight, is found by multiplying the mass by the acceleration of gravity, which when studying an object on Earth is 9.8 meters per second squared. The force of gravity is always in the negative direction, which is why the negative sign is in the formula and why the symbol J hat appears in the GlowScript code. The second part of this lab utilizes drag force, which is the force that acts in the opposite direction that the object is moving. The drag force in this experiment will be in the positive y direction because the object is falling in the negative y direction. The formula for the drag force is negative b times the square of the magnitude of the velocity of the ball. B is the proportionality constant. I chose to observe the motion of a falling plush toy using Tracker. I used the calibration stick to calibrate the position in meters from head height to the floor, and then I used the center of mass to track the object's position throughout the time interval falling in the negative y direction. The object did not travel at a constant velocity as seen by the nonlinear graph. This is the model in code from GlowScript that displays the force acting on the object if the only force was gravity. I used the initial position and initial velocity as 0 because the object was initially at rest and we had set the coordinate axis at the origin. I inputted the mass, which was 0.003 kilograms. My time step was 0.003 seconds, since that was the time between each time frame, and g is 9.8 meters per second squared, which is the acceleration of gravity. I also rearranged Newton's second law to display the velocity and position update formulas, as shown here. The second model created includes the drag force and gravity as a net force. I used the same initial conditions before with the exception of adding the proportionality constant b, which I found experimentally by comparing the final position from the observed dataset and the final position from the computational model and trying to get them as close as possible by repeatedly putting in different values for b. I also changed the values assigned to the arrow variables to run the model with the arrows showing the force of gravity, which is in orange, and the drag force, which is in blue. This next graph shows the difference between my observed data, the predicted model with only the force of gravity, and the predicted model including drag. The observed position in blue and the predicted model in red of just the force of gravity, as you can see, are similar at first, but over time their variance begins to increase, and by the end of the time interval, the predicted position is closer to the ground than the observed data. In the final graph that includes drag force, my observed position data set in blue, although still different from the predicted model, is much more aligned to the predicted model with drag than with the model with only gravity. The model that included both drag and gravity as a net force predicts terminal velocity because it demonstrated the drag force acting in the opposite direction of the force of gravity, which in this lab, drag was in the positive y direction and gravity was in the negative y direction. And over a longer period of time, these two forces would end up balancing and canceling each other out, resulting in terminal velocity. If the object were initially thrown downwards, the terminal velocity will still stay the same because it is independent of the initial velocity. And furthermore, the only difference is that if we were giving a starting velocity that was non-zero in the direction of the motion, the terminal velocity would be reached faster, and here is a graph reflecting this visually. Potential errors that could have been improved on include human error, such as when I plotted the center of mass, especially since at different time frames, the object in the video becomes blurred. Furthermore, the drag force was also experimentally predicted, so it is not as accurate as it could be. I should have also chosen an object with more drag force to get better results as well. Overall, as shown in this lab, the model that included both the force of gravity and drag was more accurate than just a graph with the force of gravity. We can see that Newton's second law can be used to predict the motion of falling objects and to predict their future positions as well.